So chapter 27 is split up into two parts, auditory and the vestibular system. We're going to start with the auditory. And before we get into the specific details of the structures within the hearing system, we're just going to talk a little bit about what sound is. And sound is any audible vibration of molecules. So it's the actual movement of molecules from the environment through the cochlea, which is the hearing organ, and then into its transduction into the brain. Right? And so if you remember all the other types of receptors that we have talked about or we're going to talk about, you have proprioception, photoreception, chemoreception. Those are all determined by the stimuli or the type of stimuli that excite those organs. And just like with touch, hearing is based on movement. If you remember in touch, which is a mechanoreceptor, we talked about Meissner's and Pacinian corpuscles, right? So those things are reliant on the actual movement of the sensing organ. And hearing is exactly the same way. And the actual sound, or what we hear, is dependent on some of these basic fundamental concepts that make up sound. Right? So those revolve around wavelength, frequency, amplitude. And the way our hearing organ is designed, it's actually capable of picking up a wide range of sounds. So sounds that vary in amplitude, vary in wavelength, vary in frequency, we're capable of sensing them at the same time. And it all comes down to the way that the structures are organized. It's very similar to a harp in the sense that you can each kind of little hair connecting is going to play a different sound is going to emanate from that, but you can play some at the same time. You can play a multitude of different times and you'll get different sounds. You'll be able to perceive or create different sounds from strumming different things at the same time. It's very similar in your ear, where if those vibrations strum different things, different structures at the same time, you're going to be able to hear this wide, rich sound. And you may be familiar with a dog whistle, right? So most humans can't hear dog whistles, and it's because that whistle elicits a pitch that's higher than 20,000 hertz, which is the maximum capacity, more or less, of our hearing capabilities. And so it's not that those vibrations aren't coming into the ear per se. They are entering. We just don't have the structures capable of being stimulated that and then transmitting that information to the brain. So the way the ears, we're going to talk about the ear, we're going to break into three different regions: the outer ear, the middle ear, and the inner ear. And the outer ear is really involved about focusing the sounds. Middle ear is really dealing with transmitting those vibrations. And then the inner ear is about transforming those vibrations from actual movement to an electrical signal. So the structures on the outer ear and that you need to be aware of are called the pinna and the auricle. Right? So they're both basically the same thing, and they're talking about the exterior part of the ear, the part that's made up of elastic cartilage. And again, they're all involved with focusing the sound. And there's also this role of protection. And a lot of those things, external parts of our body, are involved with protection, and the outer ear and the ear canal are no exception. So the ear canal, again, is going to be focusing that sound or those vibrations in towards the eardrum. They're going to be passing through that external auditory meatus and that internal auditory meatus, right? So that canal, that ear canal that's passing, that hole in the temporal bone. The ear canal also actually has something special about it as well. It has these modified sebaceous glands called carumen. And you remember we talked about sudiferous and sebaceous glands. Sebaceous glands usually secrete sebum. In the case of your ear, they secrete carumen, which again is evolved. It's evolved to trap dirt or foreign particles and kind of protect the eardrum or the tympanic membrane. Same thing. All right, so those are the basic structures that are involved with the external ear. The middle ear is a couple of bones that exist inside of it. All right, so it's got these things called ossicles, and if you look at the root of that word, ossicles, osteon, bone, all right, same thing. You have the stapes, the incus, and the malleus. They get their name because stapes looks like a stirrup, the incus looks like an anvil, and the malleus looks like a hammer or a mallet. So it's one easy way to identify which is which. And they're all about transmitting those vibrations that come through the ear canal, hit the tympanic membrane or the eardrum, and they're transmitting it to what's called an opening called the oval window. And the oval window exists basically at the entrance at the cochlea or the vestibular cochlea complex. All right, and so the only other structure within here is called the eustachian tube or the auditory tube, and that's dealing with maintaining ear pressure or air pressure. So if you go drive down to Phoenix or you take a flight, you hold your nose closed and you kind of force air back, right? And so what you're doing is you're forcing air into this auditory tube, which equalizes the pressure in the ear canal with the inner ear. And the inner ear is composed of three separate regions: the cochlea, the vestibule, and the semicircular ducts. So you can guess where it gets its name, or the vestibular cochlea gets its name. It's from these structures. And we're just going to talk about cochlea in part one, and then part two we'll be focusing on the vestibular system. So the cochlea, which means snail, is basically this curly Q of a structure that winds all the way around. And there's fluid within this structure that kind of takes those vibrations and then move it to a structure called the tectoral membrane, which it then gets transmitted to an electrical signal. All right, and so once those hair cells are set in motion, and which hair cells are set in motion, that's how information is relayed to the brain. And we'll talk about this in a little bit more detail using that schematic right there. So these fluid-filled chambers have this kind of this gelatinous material. The middle one, the scala media, is filled with endolymph. The other two are filled with perilymph. And the way that I remember that is that peri, like perimeter is around. So the perilymph is in the two outside chambers. And if you look at that image, you can see three chambers on it right off the bat, right? So you have the scala vestibuli on top, the scala media in the middle, and the scala tympani on the bottom. And I always use the scala media as my orienting point because it has all the garbage in it. It has all that stuff in there. It has the tectoral membrane. It has all the hearing. Your hearing organ is really based in there. The scala media also has the name cochlear duct. You'll see both of those used. And it just winds around like a snail shell with the scala vestibuli above it and the scala tympani below it. We'll just kind of work our way through some of the structures here. What separates the scala media and scala vestibuli is a structure either called the vestibular membrane or the Reisner's membrane. Either or are acceptable. It's not going to have a lot of attachment points. It's not going to have a lot of things attached to it. It's a really thin line for most of it. On the other end, you have the basilar membrane. And the basilar membrane, like basement, the bottom membrane, it separates the scala tympani from the scala media or the cochlear duct. And the basilar membrane is going to one that has the organ of Corti. The tectoral membrane is going to attach to it through hair cells. It's kind of got the whole action part to it. All right, and so you imagine that vibrations come through. They're going to move the tectoral membrane. They're going to affect it in different spots. Right? And the tectoral membrane is that diving board looking thing. And that's going to move hair cells at different rates and different intensities. And that's how we get the ability to hear those complex sounds. And if you ever have gone to an AC/DC concert or Justin Bieber or Selena Gomez or Modest Mouse, whatever you guys are listening to these days, and just rocked out way too hard, you stood by an amplifier and you leave there and you just hear that whoo, that ringing sound in your ear. What's happening is effectively, scientifically, you've rocked too hard. You've taken those inner hair cells, those cilia that attach the tectoral membrane and transmit that information, the wave, that sound wave information, and you've damaged them. So they're bent over and they're sending information, they're transmitting information, but just because they're damaged. But there's no kind of richness to it, there's no complexity, there's no fine grain info. So it's just that ringing sound that something's happening, we don't know what it is, but there's information being passed along. And that information is that, in the long run, is that you've damaged those hair cells. So here's a slide. This is very typical of what you're going to see in class when we look at the slides of the cochlea. You can see the cochlear duct with the tectoral membrane. In this case, the tectoral membrane is actually attached to the vestibular membrane. In most cases, it won't be. And you really can get a sense of how to organize, right? And you can see here it's labeled with endolymph, paralymph in the scala vestibuli, and the scala tympani. And really the only difference is that the concentration of potassium, more or less, there's really not too much major differences in the actual gelatinous material filling them. It's just the relative concentration of different chemicals.